So the solutions themselves to equation 7.10 are called the radial wave functions, and they depend on quantum numbers n and l. And I'm going to provide a general expression for those wave functions. So here's the general solution, and it's important to note that the L terms in here are polynomials called the associated Laguerre polynomials. And as I read it, these associated Laguerre polynomials are a function of 2r over na0. There are some ways of determining the associated Laguerre polynomials. They're also called, or sometimes called, generalized Laguerre polynomials. And for the sake of completion, I'll provide a description of those associated Laguerre polynomials that can be found on Wikipedia. And then I'm going to basically go on to say that these Laguerre polynomials are beyond the scope of the course, and later we will recognize the solutions as they are and accept those solutions. But there's a recursion formula that helps us determine the Laguerre polynomials, and this is as follows. So this is a description of the generalized or associated Laguerre polynomials, and I want to add something here to state why we're not going to go into too much detail with these. You may be relieved to hear. So this is my editorial. The textbook fails to address these polynomials. The book jumps straight to the solutions. The associated Laguerre polynomials are beyond the scope of the course, so we will just recognize the solutions and accept them. I'm going to point out at this stage that much of the math that was required in order to solve the Schrodinger equation, in fact, much of the math that was required to solve the Schrodinger equation for a number of systems that we've looked at, that math had already been developed before quantum mechanics came along. And so many of the pioneers of quantum mechanics could just dip into the mathematics from the past and actually move forward more effectively by thinking about the science with that mathematics already developed. What I will write down at this point are the first few solutions to the Schrodinger equation and these radial solutions. So I'll write down a few of these and we'll take a look in more general terms. This will tie in with what you've looked at from the Pogel work. As we look at the first solution, where n is equal to 1 and L is equal to 0, we will recognize that the Z is equal to the charge on the nucleus. We'll recognize that these solutions are applicable to many hydrogen-like atoms. These hydrogen-like atoms may have more protons in the nucleus, but they always have one electron. We're also going to recognize that this term rho in here is equal to Z times R over A0. So R20, this would be the 2s orbital. So R20, R21, These are the p orbitals with quantum number 2. And if we look at all of these solutions, all of these wave functions, solutions to the radial equation, what we need to recognize is that each is a polynomial multiplied by an exponential decay. And finally, we can note the normalization condition where we integrate over the r part of the spherical coordinate volume. Let's recognize here that our volume element d tau, if we go back to thinking about spherical coordinates and how this was set up in a previous math chapter, and again we recognize and remember that our wave function is a function of r, theta and phi is equal to r sub nl times l times y sub l. This is just a label, of course, the ml. Those were from our associated Legendre functions. And of course, the normalization condition for the hydrogen atomic wave functions is going to be given as follows. So that's our normalization condition for the entire wave function psi, and we'll come back and look at that in the next video. Thanks for your attention.